Hello, I'm Holger Lerche from University of Tübingen in Germany, and I was asked to give a talk about the genetic influences of anticonvulsive therapy in the frame of the Merit Putman Symposium at the International Epilepsy Congress in Rome in 2011. And the whole topic was the state of genetics in epilepsy of this symposium. I divided my talk into three parts, and the first part was about pharmacogenetics. There is one nice example concerning severe cutaneous skin reactions that can be due to carbamazepine. And since 2004, we know that in the South Asian population there is a specific HAL allele that can be associated, or that is associated with severe cutaneous reactions. This has been shown later on in Japan and also in Europe with slightly different alleles. And just recently, a prospective study in 5,000 patients was conducted in Japan, in Taiwan, where people that had an indication for carbamazepine treatment were tested for this specific associated allele, and the 8% of the patients that had that allele were excluded to get carbamazepine. And indeed, it could be avoided that these patients got severe cutaneous skin reactions. So that's a very nice example that population-specific testing of HL alleles is able to prevent severe allergic skin reactions or maybe other side effects. The second example, and also the third one, concern both genetic syndromes that have been described and which we do have therapeutic consequences. The first one concerns one of three sodium channels that are expressed in the mammalian brain, and this is NRV1.1. And mutations in this gene that are loss of function mutations lead to this epileptic syndrome. Since sodium channels generate the action potential, at a first glance, it seems paradoxical that a reduction in the number of action potentials can cause epilepsy. And the answer is that this is the sodium channel of inhibitory neurons, which can be shown either by immunohistochemistry, that only PAF-albumin-positive neurons, so inhibitory neurons, are stained and not the excitatory ones. And second, in mouse models where mutations have been introduced into this channel, showing that there is a reduced pattern of firing in heterozygous mice compared to the wild type. So we have a loss of inhibition, and the clinical consequence is that sodium channel blockers should be avoided in these patients. The second genetic example concerns a glucose transporter, and that's the glucose transporter that brings glucose, the main energy source of the brain, across the blood-brain barrier. And there are several syndromes. The first one is a classical one described in '91 by De Vivo, and we and others recently described other syndromes like paroxysmal exercise-induced dyskinesia on some forms of absence epilepsies that can be also caused by GLUT1. This has an important therapeutic consequence as well, because we can offer these patients a therapy that circumvents glucose as energy carrier, and this is the ketogenic diet. Ketogenic diet is 80% fat. Nobody really likes to take this, but it's a very effective therapy that takes away the seizures, that even can dramatically improve mental retardation in those patients that are only slightly retarded, that don't have the severe encephalopathy, and this is a very nice example how genetics can influence therapy. Thank you for listening.